Alright, so chapter 16 in your book begins to talk about a chemical concept known as heats of reaction. When things react, they either absorb heat. We talked about earlier that would be an endothermic reaction. Heat is absorbed in, the En of endothermic equals the in of this reaction, or they release energy. Okay, and that would be an exothermic reaction, but there are different what's called heats of reaction, and this chapter is devoted to computing those as we go. But first and foremost, we have to understand something about a term called specific heat. You were introduced to specific heat a number of, months ago at this point when we talked about the heating curve of water. The specific heat of water is the amount of heat in joules required to raise 1 gram of, in our case, water back in the day, 1 degree Celsius. And we use that to compute the slope part of the heating curves. But that idea is important. Again, the specific heat is the amount of heat in joules required to raise 1 gram of substance 1 degree Celsius. So let's try a sample problem here. It says a 4-gram sample of glass was heated from 274 Kelvin to 314 Kelvin, a temperature increase of 40 Kelvin, and was found to absorb 32 joules of energy as heat. What is the specific heat of this type of glass, and how much energy will the same glass gain when it is heated from 314 to 344 Kelvin? Okay, so not only do you know the definition of specific heat, but the actual formula to compute specific heat is Cp, that's specific heat, is a function of Q, which is the energy lost or gained, divided by the mass of the sample times the change in the temperature of the sample. So take a minute, okay, and the moderator, you can pause if need be, but take a minute to write down the equation Cp equals Q divided by M times change in T, okay, and write down what all those things mean, because we are going to go on and solve this problem. So pause here if need be. Okay, so in order to solve this, in A, we just simply plug in what we have here, and we come away with Cp, the specific heat of this, will be the amount of heat that's released, in this case 32 joules, divided by the mass of the sample. This glass, or this sample of glass, is 4 grams, times the temperature change. Our temperature goes from 274 Kelvin to 314 Kelvin. That's a change of 40 Kelvin. You multiply 4 times 40 and divide 32 by that number to get 0.2 joules per gram times degrees Celsius. Or excuse me, joules per gram times Kelvin. Okay, there is a specific heat that allows you to multiply times degrees Celsius, but we're dealing with Kelvin, so we're going to keep it in Kelvin. All right, so that's the answer to A. What about B? How much energy will the same glass sample gain when it is heated from 314 Kelvin to 344 Kelvin? Okay, now we're solving for Q, the energy gain, okay, but we already know, we just computed the specific heat. And the specific heat of this, because it's the same glass sample, it's not going to change. It's 0.20 joules per gram times Kelvin. Now, I told you back in the day when we did talk about the heating curve of water that the specific heat of a substance is a physical property. I mean, it doesn't change based on the quantity you have. It's a part of its identity. Okay, so this piece of glass, any sample of it will essentially have a specific heat of 0.2 joules per gram times Kelvin. Okay, so what we have to do for B is just essentially rearrange the equation so we get the heat lost, okay, equals the specific heat times the mass of the sample times the temperature change, okay, which in this case we just computed the specific heat at 0.20 joules per gram times Kelvin, multiplied by the sample. Again, it's 4 grams, and now our temperature change is 30 Kelvin. Notice that's 24 joules, but notice also how these things cancel out nicely. Okay, we have 0.2. Notice, okay, grams is in the numerator here, it's in the denominator here, that comes out. Okay, and then Kelvin is in the denominator here, it's in the numerator here, so they fall out, leaving us with a desired unit of joules. Okay, so when you set these things up correct mathematically, things work out as they should. So that's a sample problem on how to deal with specific heat. Okay, but moving on, let's talk about our first graph here. As you can see, this is an endothermic reaction. Okay, so it's an exothermic reaction pathway. And I just want to draw your attention to a few things as we do this. In an exothermic reaction, okay, the reactants have more energy than the products. Okay, this down here is the course of reaction. This is the enthalpy. Okay, so on the x-axis is just essentially time. On the y-axis is heat. Enthalpy is just a fancy word for heat. Okay, so make a note of that. Enthalpy is a fancy word for heat. But notice that's written on the y-axis, so you can see when we first start here, our reactants are at a higher energy level than our products. Okay, I see that my recording left off here, so I'm not sure where, but we were talking about exothermic. I apologize for that. Talking about exothermic reactions. Okay, we came to this. If this is repeated, so be it. But the change of heat for an overall reaction is really the products. The change in heat of the products minus change heat of the reactants. Okay, and as you can see here, the products are at a lot less lower energy state than the reactants. Okay, so if I were to subtract a small number here from a large number here, I'm going to come away with a negative value for my overall change in the heat of this reaction, and therefore, again, H is negative with exothermic reactions. Okay, these, moving on a slide here, these are actually favored in nature. Let me explain that. Anything that releases energy, by definition, will have a negative number here. In the case of the formation of water, negative 483.6 kilojoules, is released when I combine the constituent molecules to make water. When I combine 2 moles of hydrogen plus 1 mole of oxygen, I produce 2 moles of water, and in the process, I release a large amount of energy. In fact, we can almost write this in and say plus 483.6 kilojoules. So we can say, literally write that in as a product. So anything that favors the release of energy, for the most part, is going to be favored by nature. Now, I say that with a modifier. When we get to the end of this presentation, we'll talk about something called Gibbs free energy, and that equation takes into account not just the heat that's released in case of an exothermic reaction, but it also takes into account another product called entropy, which is a measure of the randomness or disorder of a system. So really, thermodynamically speaking, and I'll repeat this a little bit later into the presentation, but thermodynamically speaking, really in God's created order, everything's at a balance between low energy and high entropy. Okay, so things want to have as low energy as possible. So in this case, with the reactants becoming the water product is at a very much more stable state in terms of energy. It's got a lower energy than the 2 reactants, and therefore it's favored. Okay, so you're going to have a release of 483.6 kilojoules, which is a huge energy release. So this is favored the forward process. Okay, and in a few minutes we'll talk about entropy and how that balances things out. But that's the exothermic pathway. I want you to be familiar with this graph here, okay, and be able to do things with it and read it. And I want you to be familiar with the overall quick and easy way to figure out the change in H, or the change in heat of enthalpy of a system. And I want you to have an example here. But moving on, we can talk next about the endothermic pathway. Okay, the endothermic pathway is the exact opposite of what we've been talking about here. Okay, as you can see in the endothermic pathway, the reactants are at a much lower state than the products are. Okay, the products that are higher energy. So in order for this to move forward from reactant to product, we need to supply the system with energy, with heat. Okay, that's the only way to move this from one to the other. Okay, and for quick and easy understanding of this, we can look at the reverse process of water. Moving forward, if I can form water from its constituent molecules, I release energy. Well, same logic applies that if I were to break water down back into hydrogen and oxygen, I have to add energy to the system, and conveniently enough, it's the same amount of energy that I needed, that was released when I form water. That amount of energy released is going to be the amount of energy absorbed to essentially lyse water. That's the special word, electrolysis. Use electricity to lyse the water molecule into its constituent molecules of hydrogen gas and oxygen gas. So that's an endothermic. It's the exact opposite of exothermic. And exo means energy is released in the system. It exits the system. Think EX of exothermic, the EX of exit. And then endothermic, energy is absorbed, IN, or EN in endothermic. So hopefully that's a little mnemonic to help you remember that. But that's how you do these problems. Now, when we talk about thermochemical equations, and that's just a great name here, okay, but that's what we're going to start talking about, some thermochemical equations now. Okay, a few things to remember. The coefficients in a balanced thermochemical equation represent the number of moles of reactant and products and never the number of molecules. This allows us to write these coefficients as fractions rather than whole numbers when necessary. And that will become necessary, as we'll see in a few minutes. Number 2, the physical state of the product or reactant involved in a reaction is an important factor and therefore must be included in the thermochemical equation. So you have to put in parentheses as subscripts the physical states for these problems. Number 3, the change in enthalpy, or the heat change, is represented by a thermochemical equation, is directly proportional to the number of moles of substances undergoing a change. For example, if 2 moles of water decompose, twice as much enthalpy, 483.6 kilojoules, is needed than the decomposition of 1 mole of water. Okay, where do we get this value? They are provided in 2 different tables, okay, at the back of your book. For test, I will include to your helps those 2 tables so that you're able to compute these problems, okay? And you'll get a little bit more savvy with these appendix. They're actually tables in the appendix, okay? We'll talk about that in a second. All right, number 4, the value of the enthalpy change in H, is usually not significantly influenced by changing temperature. So it really doesn't have that much of an impact, the temperature change. Those are a few, I guess 4 guiding principles when we talk about some of these reactions. What I wanted to show you is how this is called a coulometer, okay? And it said, it shows how this would be worked out, okay? A weighted sample is ignited by an electric spark and burned in a sample dish in an atmosphere of pure oxygen, okay? So you have this sample dish down here, okay? And there's a sample in there, it's burned, okay, pure oxygen. Oxygen is what combusts things, okay. The energy generated by the combustion reaction warms the steel bomb and the water surrounding it. Okay, so again, you have the steel bomb here, you can see that. And there's water surrounding it, then there's a thermometer to essentially measure the initial and final temperature, which is then able to compute the temperature change, and that'll tell us how much heat is involved. So this is what's called the simple combustion calorimeter. Can't say it right now. Okay, but that's essentially what we use. All right, and there are 2 things that we need to be aware of. Okay, the enthalpy of formation and the enthalpy of combustion. Essentially, these 2 things, enthalpy of formation is the amount of heat needed, okay, to create 1 mole of a substance. Enthalpy of combustion is the amount of heat created when you essentially burn 1 mole of a substance. So those are the quick definitions, okay? Why don't you pause the video right now, all right, and go into your books, open to chapter 15, and write down the technical definitions of enthalpy of formation and enthalpy of combustion. Take a moment now. Okay, welcome back. Now we're going to talk about Hess's law, which is really all-important law when it comes to computing some of these things. He says, Hess, the overall enthalpy change in a reaction is equal to the sum of the enthalpy changes for the individual steps in the process. Okay, the overall enthalpy is essentially the sum of its parts. Okay, is equal to the sum of enthalpy changes for the individual steps in the process. So whether something is going to be exothermic and ultimately end up with a negative change in H, or something is endothermic and will ultimately end up with a positive change in H, really depends on the steps that make up the overall reaction. Okay, what does that look like? Well, here is how we're going to compute this. This is a rather long formula, but it says essentially the change in heat of the enthalpy is really the sum of the change in heat of formation of the products times the number of moles of products minus, again, this is just a special version, if you'll remember, of the change in H equals the change in H of the products, so we'll call it P, minus the change in H of the reactants, which we'll call R. Okay, so this is just a longer version of this. Now we have the change in H of the products times the moles of products minus the sum of the change in H of the reactants minus the moles of the reaction. So as I said, this longer equation is just a more descriptive picture or definition of what we got going here. All right, but Hess's law is very important. It says the overall enthalpy change in a reaction is equal to the sum of the enthalpy changes for the individual steps in the process. Okay, so let's try an example of this. Okay, here we go. We have calculate the enthalpy of reaction, okay, for the combustion of nitrogen monoxide gas, NO, to form nitrogen dioxide gas, NO2, as given in the following thermochemical equations. So this is going to be our all-important equation here. NO gas, again, one of the parameters of doing these problems is to put the physical states in there. So nitrogen monoxide gas plus half a mole, okay, not a half a molecule, there's no such thing. A half a mole of oxygen as a gas will yield 1 mole of nitrogen dioxide as a gas. That's our general equation. Now we're trying to figure out what the overall change in heat of enthalpy will be. So we're told to use the enthalpy of formation data in appendix table A14. So you got to use that in the back of your book. There's an appendix section. Find table A14, and you'll be able to find all the miniature, what is called that, almost half reactions, half steps for these things. Solve by combining the known thermochemical equations. Verify the result by using the general equation for finding enthalpies of reaction from enthalpies of formation. Okay, so when you go to the back of the book, you find some given information here. I'm going to write these things down. I'm going to stop the presentation as we go and talk about this a little bit. Okay, so when you go to the back of the book, this appendix A14, you find that in order to form NO gas, okay, you need to react. That's his first line here. In order to form NO gas, you need to react a half a mole of nitrogen gas with a half a mole of oxygen gas. Now you ask yourselves, well, why do I need to figure out how much nitrogen monoxide releases? By the way, that would be an exothermic reaction where almost 91, just over 90 kilojoules is needed to be added to the reaction in order to make this happen. But you say, well, but I'm not trying to do that. I'm trying to figure out NO2. And the reason why I have to start with NO is because you don't have in appendix table A14, you don't have anything going directly. Well, let me strike that. You need to start out with NO because you have as reactant here a nitrogen monoxide. Okay, so you need to account for how much it's going to cost essentially to create nitrogen dioxide. And as you can see here, it takes just over 90 kilojoules to create that. Okay, so you got to start with that one for those reasons. Okay, the other thing you can find on that table is the second reaction here, which says now if I take a half a mole of nitrogen gas plus a whole mole of oxygen gas, then I get my desired unit of NO2. Okay, so in order to figure out how much NO2, how much energy is needed to produce a mole of NO2, if I simply were given nitrogen and oxygen, I can tell you immediately that it'll take 33.2 kilojoules. But that's not what's being asked here. What's being asked here is if I were to combust NO. In other words, if I were to burn NO, how much is the overall heat of energy in order to burning NO in oxygen to form NO2? Okay, so those are the two pieces of this puzzle that you're going to need. Okay, so that's the first step of what you want to do here. The second step, okay, notice real quick, desired reaction involves NO plus a half mole of oxygen as your reactants, and then your NO2 as a product. So that's the stipulation. I just want to draw your attention to that. Again, this would be a lot easier, going from nitrogen, oxygen, and then forming nitrogen dioxide, but that's not what the reaction is calling for. The reaction is actually calling for this up here. If I start with nitrogen monoxide, that's a different thing. So just notice, desired reaction involves as reactants nitrogen monoxide and a half mole of oxygen gas, and the desired product is nitrogen dioxide. Okay, so since NO, the gas as a gas, is a product, okay, I'm sorry, is a reactant, okay, since nitrogen monoxide is reactant in our equation here, all right, we reverse the first reaction and the sign for the heat of formation, okay, so here I have this first reaction here. I've got to reverse it now, okay, because I'm not looking for nitrogen monoxide as a product, I'm looking as a reactant. So I got a reverse reaction and then reverse this sign from positive 90 to negative 90. So when I do that, down here, essentially this is going to be an exothermic reaction because NO is a reactant, not a product, okay? Secondly, since the other equation has NO2 as gas as a product, we just keep it as is. There's no need to reverse either the reaction itself or the sign on the change in F, change in HF, which was given as positive 32.2 kilojoules. Okay? So, because, long story short, because NO is a reactant and not a product, we reverse its reaction and its sign, but because NO2 is is a product and not a reactant, we can keep the other thing as is. Okay, now in our solution, we invoke Hess's law. Okay, and Hess's law says let's add the two equations together. So when we do that, this is what we come away with. We have nitrogen monoxide in blue here, okay, as a reactant. We draw the reverse of the initial equation and we reverse its sign, and then we keep in red, okay, the forward equation for the formation of nitrogen dioxide. Okay. What we do next is we add these essentially together, okay? So let me take you through that. Notice first that I've got nitrogen as a product there and as a reactant here, so it cancels out. Then I've got, notice, half a mole of oxygen here and an entire mole of oxygen there, so I'm left not with a canceled out oxygen, but with half a mole of oxygen as reactant in my overall final equation, okay? And then my product, in this case, is nitrogen dioxide. What I also do is I add my individual heats of formation up. So I essentially end up subtracting 33.2 from 90.29 to come up with my negative 57.1 kilojoules. This negative value means that this is favored in nature and it will happen. Okay? All right, if you need to review that, you can. This will also be posted at home for homework. Okay, let's talk about another problem here. All right. This one says, give me a second here. Okay, this one says calculate the enthalpy of formation of pentane C5H12 using the information on enthalpies of information in appendix table A14 and the information on enthalpies of combustion in appendix table A5, solved by combining the known and thermochemical equations. Okay, so why don't you pause the equation here, get together in partners, okay, and then I'll come take a few minutes when everybody's done, replay the presentation, and I'll explain how to get the answer here. Okay, pause it now. Okay, welcome back. Let's go through this, okay? These problems are in the book, but here we go, okay? We use Appendix Table A14 and Appendix Table A5 in the back of the book to figure these out, okay? So given the formation of carbon dioxide from its elements carbon and oxygen, okay? Carbon as a solid plus oxygen as a gas yields carbon dioxide gas, and it releases 393.5 kilojoules. Okay, in order to form water, we've already done this one, but water, hydrogen gas plus half a mole of oxygen gas gets us 1 mole of liquid water, and it has a release, or it's exothermic, with a negative 285.8 kilojoule release. And then finally, this last one here, okay, is the actual combustion of, in this case, pentane. I need for every 1 mole of pentane, I need 8 moles of oxygen plus 5 moles of carbon dioxide plus 6 moles of water are produced. So the unknown is the change of heat of formation for essentially that last line. Essentially, well, not the last line, but 5 moles of carbon plus 6 moles of hydrogen equals 1 mole of the C5H12. Why does it eliminate all those other things? Because they essentially get eliminated as you go through. Okay? Carbon dioxide and everything else comes out when you do this. So this is really the overall unknown equation that we have here, is this one here. Okay, this is what we're looking to do. Let me do that again. Okay, that's what we're looking for. Change of heat of formation for 5 moles of carbon plus 6 moles of hydrogen gas, yielding 1 mole of our pentane gas. Okay, so combine the given equations according to Hess's law. We need C5H12 as a product, so we reverse the equation for the combustion of C5H12, because this is not a product here. Okay, C5H12 is reactant here, so we've got to reverse that equation, okay, and reverse the sign in each this. Reverse that sign, because this here is pentane's a reactant. We want it as a product, so in order to reverse the equation, we've got to reverse the sign as well. And we multiply the equation for formation of CO2 by 5 to give 5 C's as reactant, because that's what we want here. Okay, I have, notice, 5 carbon, excuse me, that's not the right thing. I have 5 carbon in my pentane, so I need 5 moles of that stuff. And then I multiply the equation for formation of H2O by 6 to give 6 moles of my hydrogen. Again, I have 6 moles of that bad boy there. So I've got to do some adjusting as is. So I take the equations that I'm given. The first one, as I stipulated, I multiply it by 5. Everything has to be multiplied by 5, okay, because I need 5 moles of carbon, because I have 5 carbon moles and 1 mole of pentane. Okay, because I multiplied everything across by 5, I will also multiply the change in heat of formation by 5. Okay, I do the same thing down here when it comes to formation of water, more specifically my hydrogen. I need 6 moles of my hydrogen, because that's how much I have to react in order to produce the pentane. Okay, and then because I multiply 6. Again, we're looking at the second equation here, and the second equation says, for every 1 mole, look up here real quick, for every 1 mole of hydrogen, it's 1 to a half. So if I start with 6, I got to multiply 6 times a half is 3, and then this last one here is a 1 to 1. And then the last thing that we have to do is take this last process here. Okay, this is a reverse. Remember, we reverse this reaction here. That's the forward reaction. Now we got to reverse it and its sign. So I'm taking 5 moles of carbon dioxide plus 6 moles of water and producing 1 mole of pentane with the energy change in plus 3,535. Okay, so when I take all that in and I subtract out where I need to subtract out, I come away with, notice, this comes out, okay? This comes out, this, and I'm left with what I predicted, okay, up here. All right, and when I take all these into account, I come away with a final answer of negative 146.7 kilojoules. So there's energy released overall in that process from doing that, okay? So that's how to do this second type of problem. All right, hopefully you had a chance to do that. Why don't you pause and take down some of those points and those steps if you need to now. Pause. Okay, welcome back. What I want you to do now, okay, is work on these section review changes, or for section review problems 1 through 6. So you can pause the video. Actually, make sure you finish the video. This will be part of your homework. Okay, so don't pause the video yet, but students, I require you to do 1 through 6 of this. Actually, we're only about 30 minutes in, probably about a little over a period. And so why don't you stop for a few minutes and do this, and give 15-20 minutes proctor depending on time. Okay, we can pause now. Okay, welcome back. This is the last portion, last little bit of information I want you to know from chapter 16 about reaction energies. All right, and that involves a whole new formula. Okay, and that formula is a change in G with the superscript of 0 equals a change in H with a superscript of 0 minus T, which is temperature in Kelvin, times the change in S, the superscript of 0. And as I alluded to in the beginning, this is where everything comes together. Change in G, you can write it down, is the change in Gibbs free energy. Change in H is the change in the heat, or the enthalpy. Minus T is the change in temperature as given in Kelvin, and the change in S is something called the change in entropy. Now, thermodynamically speaking, I'm going to keep this very simple for you. There are essentially two laws of thermodynamics that govern living things. The first one involves heat, okay? The change in H, all right? And by general rule of thumb, everything in nature strives for the lowest energy state possible. Okay, and the second law of thermodynamics, which is the change in entropy, is a measure of the randomness or disorder in a system. And all things in nature strive for high disorder. Going back, way back, I guess, in our discussion in chapter 10, when we talked about solid, liquids, and gases and the states of matter, we said that gas has by far the most disorder, the most randomness, therefore the highest entropy. But because they have such high entropy, they also have high energy. Usually the two go hand in hand. Okay, whereas solids, the other side of the spectrum, they have low energy, they're very stable energetically, but they're also very ordered. Okay, which things in nature do not prefer that. I personally think that this entropy issue came at the end of Genesis 3, when God essentially banished man to a realm where change was possible, and with change comes decay, because really change in S, or entropy, is just a measure of decay. It's a measure of randomness. You know, it took a number of years for the World Trade Center to be built back in 1975-76 when they started. It took a matter of minutes for it to fall down, both of them. Right, that's a picture of things striving for high energy. Another great picture is probably your bedroom. If you don't maintain some control over it, it'll get real dirty, real messy in really no time. So those are examples of things striving for high degree of disorder or randomness. But again, in nature, we find kind of like a bargaining system. With gases, okay, we'll take the high energy. Because we want high entropy, and with solids, it's we'll take the low disorder, low entropy, because we have also low energy. So it's a balance here. So really, the best indicator of whether a reaction will actually go to completion in nature, we'll see in a minute, is really a balance between the energy gain, or the energy compromise and the entropy compromise. Okay, so let's look at this problem. For the reaction of ammonium chloride solid ammonium chloride decomposing into ammonia gas and hydrochloric acid as a gas at 298.15 Kelvin, so it's a set temperature, the change in H of this reaction, okay, the change in H factor of this equation here is 176 kilojoules per mole, and the change of S of this reaction is 0.285 kilojoules per mole times Kelvin. So let's calculate the change in G and tell whether this reaction is spontaneous in the forward direction at 298.15 Kelvin. So this is going to happen at a constant Kelvin temperature, and we need to know what that temperature is because that's the T part of this. So this is a matter of just writing down your given information and plugging in. All right, it's really easy. Given information, change in H is 176 kilojoules per mole at that temperature. The change in S is 0.285 kilojoules per mole times Kelvin at that specific 298.15 Kelvin. The unknown is the change in G at that temperature. So I have change in S, change in S, change in S, change in H, T, and I'm trying to find the change in G. So we simply use the equation I just had written out right here, and we plug everything we know in. That's the first line, okay? 176 kilojoules minus 298 Kelvin times 0.285 kilojoules per mole times Kelvin. Following order of operations, we would multiply first, and then when we do that, we essentially subtract 84.9 from 176, and we come up with a simple answer of 91 kilojoules per mole. Because that's a positive value, this is not a spontaneous reaction in nature, okay? This is ultimately endothermic. Okay, it's not going to happen spontaneously. There's going to be need of energy or a catalyst. Something needs to be added to the system to make that happen. All right, ladies and gentlemen, that is about it. The only other thing that I want you to do now is, if there's time, again, the presentation is over, so you can work on these 7-section review problems. Okay, look online also for homework, which will include you finishing these and maybe a few extra from the chapter review. But that, in a nutshell, in 38 minutes, is essentially heats a reaction. Okay, so we will have time on Friday to review these things. This message will essentially be posted online, so you can skim through it, fast forward to the points you don't understand, so you can finish your homework. But we will review this material on Friday. God bless you. Have a great day.